Hi everyone. In this video, we will work out a couple of problems from Tipler and Mosca's Chapter 16 exercises. The two problems that I've picked are also in your tutorial 16.5. They're problems number 16.46 and 16.69. So let's start with 16.46. And for this problem, in the book, you will find that the book gives numbers for the problem, and I have taken each of those numbers and replaced it by a letter. So, for example, this problem says using some number for the speed of sound in air, and I have replaced that with v. And then using v for the for the speed of sound in air, calculate the fundamental frequency for an organ pipe of length L. Again, the length, the actual value is given. We're going to work this problem out with L. With the following characteristics. So for part A, it's a pipe that is open at both ends, and for part B, it's closed at one end. Okay, so let's see how to solve this problem, right? So we have to find the fundamental frequency. So 46A, so this example is an example where we have an organ pipe which is open at both ends. So let's draw a picture. So this is our pipe, and it's open at both ends. And since it's open at both ends, when a standing wave forms inside this, right, it must have a pressure antinode at both ends, right? So if it's a fundamental frequency, that means that the wavelength is the largest, which means that it will have an antinode at each end, but have only one node in the middle. So if I wanted to draw the wave pattern, this is what it's going to look like, right? So two antinodes, antinode at the two ends, right? And this one is a node, right? Node in the middle. Okay, great. So what else do we know about this pipe? We know that its length is given, that length is L, and we know that since this is a standing wave pattern, we can go back to our favorite wave pattern sort of symbolic way of showing it. Starting from this point all the way to here, that is one wavelength, lambda, right? But in this particular problem, we have two consecutive antinodes that is separated by one node. So, so the picture over here is just this part, right? And that distance is lambda over 2, half the wavelength, right? So that tells us that L must be equal to lambda over 2, okay? Or we can also write this as lambda is equal to 2L. Great. Now we also know the relationship between speed of sound, frequency, and wavelength. And that relationship is V, speed of sound, is equal to frequency multiplied by wavelength lambda. All right. We also know what lambda is in terms of the length, that is equal to 2L. So let's plug that in. So we have F times 2L, or which is equal to 2FL. Eventually we have to find F. So let's turn this equation around and we can write this as F is equal to V divided by 2L, right? All I did was divide both sides of this equation over here by 2L, and so I get F equals V over 2L. And this is the fundamental frequency that we need. Okay, so this is the fundamental frequency in this case. In this case, our pipe is an open pipe. And what does that mean? Well, it means that open at both ends. Okay, so open pipes are open at both ends. All right, so that's part A. So now let's look into part B. Part B is for a closed at one end pipe. And these pipes are often referred to as just closed pipes, right? Open is open at both ends, closed is open at one end. Okay, so this is the picture. It's open at one end and closed at the other end, right? So whenever there's a closed end, that's where a pressure node forms, right? And there's an antinode at the open end. So then again, since we are interested in the fundamental, which is the largest wavelength, and that can happen if we just start with an antinode here and go straight down to a node there, right? So this is what the standing wave pattern would look like. And again, if we go back to our formula here, the distance between a node and the closest antinode is just a fourth of the wavelength, lambda over 4. So this distance, right? So this distance is L, but is also equal to lambda over 4, right? Because this is a node and this is the closest antinode, right? Great, so L equals lambda over 4, which also tells us that lambda must be equal to 4L, okay? So if lambda is equal to 4L, we can again use this relationship between V, F, and lambda. We get V equals F times lambda, which is equal to F times 4L, or 4FL, and then I can divide both sides of this equation by 4L, so that would give me F is equal to V over 4L. Great. So this is our answer for the fundamental frequency for a closed organ pipe. Closed pipe. So closed organ pipe meaning closed at one end, right? So it's closed at one end. Okay, so that's how we work out the answers for problem number 46. Our next goal would be to address problem 69. So let's first read the statement of the problem. It says, working for a small gold mining company, you stumble across an abandoned mine shaft that, because of decaying wood shoring, looks too dangerous to explore in person. To measure its depth, so this is the first place where the problem tells you what you need to find. It's you're measuring the depth of a mine shaft, and you're going to employ an audio oscillator of variable frequency, right? So you determine that successive resonances are produced at frequencies of, you're going to use labels for them instead of the numbers that are given, and then eventually we'll plug these numbers back in to figure out the numeric answer. And the idea is to estimate the depth of the shaft, right? Okay, so you're wanting to find the depth of the shaft, right? So first we have to determine what this problem is. It doesn't tell you anything really about what you're doing, so it can be a little bit confusing, but you can think of this like you can sort of think of a simple picture for an abandoned mine shaft, right? So what does a mine shaft look like? Well, it's a shaft looking like this, like a pipe, and then at the bottom of the shaft, because this is a mine, there's nowhere to go, right? So the bottom is kind of closed off, but the top is open because then miners can get into the mine, right? So this kind of looks like an open pipe, yeah? So this is an open pipe, and the length of the open pipe, which is same as the depth of the mine. And so we are essentially, this problem is all about standing waves in an open pipe, and we are finding the depth of the mine, which is the same as the length of this open pipe here. Okay, so how are we going to measure the depth? Well, it turns out that we hear successive resonances. What does this mean? Well, it tells us that when we put in sound in the shaft, it's gonna oscillate and form standing waves. And when it forms standing waves, that's gonna resonate, and that's the frequency that essentially you're gonna hear as the resonant frequencies, right? And it also tells you that these are two successive resonances. Okay, so since these are successive resonances, these are probably harmonics that are consecutive in the spectrum of harmonics for the closed pipe, that is this mine shaft. Okay, so we are essentially then going to find a relationship between the depth of the mine and these frequencies that are given to us. Okay, so let's take F1 and F2, and since we know F1 and F2, we can find delta F, which is equal to the difference, F2 minus F1, which is the positive difference between these two frequencies. Okay. What kind of waves can resonate in this closed pipe? Well, we know how a closed pipe works. We know that the top end of the mine, that has to be a pressure antinode, so there has to be an antinode over here, and there has to be a node at the bottom which is closed, right? So that means that the formed waves could look like this. That would be the fundamental. And then you could have a harmonic and higher harmonics, of course. Now, the tricky part of this problem is that we don't know which of these frequencies is either from harmonics or whether they're fundamental or anything, right? This information is not given to us. So what we're going to do is we're going to come up with a general formula to tackle this problem. So we know that the harmonic if one of them were the harmonic, then for that particular standing wave, then we can write d equals lambda over 4, right? Because lambda over 4 is the distance between the antinode and the closest node, which happens when you have the fundamental frequency, right? Okay, but d could also be equal to 3 lambda over 4, and this would be for the first harmonic. And we can keep going, but generally d would be equal to 2n minus 1 lambda over 4, right? Okay, so that tells us, and 2n minus 1 lambda over 4 for the nth lambda. So we should have probably written over here, we can write lambda 1 and lambda 2, etc. Right? So when n equals 1, this will give you lambda 1 over 4, etc. So lambda n then looks like 4d over 2n minus 1. All right, and then we know that the frequency, nth frequency, fn, must be equal to v over lambda, right? That's the relationship between frequency, speed of sound, and wavelength. So this equals v divided by lambda n is just 4d over 2n minus 1, right? So if I just plug this in and bring the 2n minus 1 to the numerator by flipping it, so we get 2n minus 1 times v over 4d. Okay, so this is one of the frequencies. We know the difference between two consecutive frequencies, so let's work out the next frequency, the next harmonic after this. So we want to work out fn plus 1. Now that is quite simple because we can just take this formula for fn and replace n by n plus 1 on the right hand side. So we get 2 times n plus 1 minus 1. So all I did was wherever n appeared, I put in n plus 1, right? Times v over 4d. All right, so I can simplify this stuff within the parentheses, and this turns out to be 2n plus 2 minus 1, which is 2n plus 1 times v over 4d. Okay, so these are two consecutive harmonics, right? Harmonic frequencies for the closed pipe. But what we're interested in is really the difference between them. So delta f is equal to fn plus 1 minus fn. And we are doing this because we don't know if we don't know the value of n for either of these given frequencies, right? But we know that they're successive frequencies, which means that they have to be coming from consecutive harmonics. So fn plus 1 minus fn, so that now we can just plug in these results. So we get 2n plus 1 times v over 4d minus 2n minus 1 times v over 4d. We can factor the v over 4d out, so that will give us 2n plus 1 minus 2n plus 1, and this plus sign comes from the fact that I distributed the negative sign into the parentheses, so I get negative 2n plus 1. Okay, so the 2n and the minus 2n will cancel, so we will have v over 4d multiplied by 2, and this 2 will cancel with the 4 in the denominator, so eventually we get something that looks like v over 2d. All right, now I can flip this equation around because eventually I need to find the depth of the mine. So D equals V over 2 times delta F. And that's our result, right? But remember, delta F is just F2 minus F1. So this is V over 2 times F2 minus F1, right? So this is our result in terms of just symbols. But I want to go one step further, and I want to actually work out the numbers for this particular problem. So let's do that. So let's plug things in. So we have D is equal to V. We know the speed of sound. So V, speed of sound in air, is roughly 343 meter per second. Okay. So this is the speed of sound in air. So this is an important piece of information that is kind of not given in this problem, but you're expected to either look this up somewhere or know it. So D is equal to V over 2 times F2 minus F1. So let's plug in V equals 343 meter per second divided by 2 times F2 minus F1. Let's go to the problem. F2 is 52.10 hertz. So this is 52.10 hertz minus 31.26 hertz. Okay, so now notice that this 1/2 in the numerator cancels with the hertz in the denominator, right? Because hertz is nothing but it's equivalent to second inverse, right? So those two cancel, so that our result would be now in just meters, which is good, right? Just meters. All right, now if you do this calculation, plug these numbers into your calculator, you'll find that this is equal to 8.23 meter. So that is our D. So the depth of the mine is 8.23 meters, and that's all the problem is asking for. Great, but I want to go one step further, and we can actually figure out some more information from this problem. And the main thing that I want to figure out is to check what harmonics these two frequencies that are given to us are, right? What harmonics? So what harmonics, and what I mean by this is it fundamental or first harmonic, etc. We never use this information anywhere in the problem, but we can sort of extract this information from the problem. Okay, so how do we do that? Okay, so let's go back and go back to our formula for Fn, right? So we know that Fn is equal to 2n minus 1 times V over 4D. And let's also look at the result that we found, which is D is equal to V over 2 times F2 minus F1, right? We can actually turn the second equation around and write F2 minus F1, that is equal to V over 2D, right? So now let's go back to this equation. We can have 2n minus 1 divided by 2 times V over 2D. So I just separated the 4 out into 2 factors of 2. And then I'm going to plug in V over 2D is equal to F2 minus F1. So this is equal to 2n minus 1 over 2 times F2 minus F1, right? So then if I turn this around and I want to find n, so 2n minus 1 is equal to 2 times Fn divided by F2 minus F1. And in this particular case, although I'm using Fn, what I really mean over here is the lower frequency that is given, which is this 1, right? F1 that is given to us. So this is nothing but F1. Okay, so if I keep going and try to isolate n, so this is 2n, so I'm going to add 1 to both sides, so we have 1 plus 2f1 over f2 minus f1, and I'm going to bring the denominator together, make it a common denominator, so we get f2 minus f1 plus 2f1 in the numerator. This negative f1 will cancel one of the f1s and the 2f1, so we get f2 plus f1 divided by f2 minus f1. Okay, so now it's simple. So the final result is n is equal to 1/2 of f1 or f2 plus f1 divided by f2 minus f1. Okay, so at this point we can plug in our numbers. So we have 1/2 multiplied by f2 is equal to 52.10 hertz, 52.10 plus and the other one was 31.26 divided by 52.10 minus 31.26. And note that since these are both the numerator and denominator are just frequencies, so we don't even have to write the units. If we did, we would have hertz in both the numerator and the denominator, and both will cancel. Right? So now if you do this calculation in your calculator, you will see that this number is equal to 2. So we found that n is equal to 2. So what does that mean? So n equals 2 tells us that this is the first harmonic, right? So this standing wave is the first harmonic, which means that the next one, which is the other one that is given to us, that is n equals 3, is the second harmonic. So the resonant frequencies that we just measured in that in the mine shaft, they are the first and second harmonics. This does not include the fundamental, right? So if anyway you started, so it's not the fundamental, right? So if you started this problem by assuming that the lower frequency was the fundamental frequency, then that would give you a wrong result. All right, so that's kind of the crucial point in this problem. And that's also, we can actually use this problem also to figure out the number of the harmonics in this problem. Okay, so that's it for this video. If you have questions about it, please email me at bhattach@ltu.edu. Thanks a lot.